Hello everyone. In this video, we'll be going through the topic transformation of functions. So this topic is divided into two parts. In part A, we'll briefly discuss how to perform translations and logarithmic transformations, as well as to discuss three problem sets. And the two remaining questions will be left for discussion in part B. So part A right now. So this is a summary table about performing vertical and horizontal translations of a given function. So let's start with vertical translation first. If you would like to translate the graph upwards by k units, then you just need to add the constant k outside the function f. As you can see, y equals to fx plus k will be the function that you would like to obtain. For translating the graph downwards by k units, something similar. It will be y equals to fx minus k. As you can see here, for vertical translation, the constant k is actually added outside the function f. What about horizontal translations to translate the graph leftwards or rightwards? This time, the constant k has to be incorporated inside the function f. The k is next to the independent variable x. So if you'd like to translate the graph leftwards, it will be y equals to f x plus k. Whereas translating the graph rightwards by k units, it will be y equals to f x minus k. So the strange thing for horizontal translation is that if you like to translate the graph leftwards, you are adding a constant. Whereas if you are translating the graph rightwards, you are actually subtracting something next to x. So this is about the translation of functions. And finally, about the logarithmic transformations. So I would like to take this opportunity to relate the mathematical technique of logarithmic transformation with the elasticity of demand. So if we have a demand function in the form p to the power k times q equals to a constant, we know that this demand function will have a constant elasticity at negative k, the negative of the power of p. So sometimes the question will give you the log form of this kind of demand function, which would be expressed in this form after performing logarithmic transformation. If you're trying to plot log q against log p, then this equation is actually a straight line with a slope of negative k. So what is the takeaway? If both the independent variable in consideration and the dependent variable are both in log form, then we can automatically find out the elasticity, which is the coefficient in front of the log p here. So that's all for the review part, and we'll move on to the discussion question. We have the first one here, given the demand and supply equations of live chickens. So if the government predicts that the quantity supplied will increase by 30 million chickens at any price due to the import, so what will be the new market equilibrium price and equilibrium quantity of chicken? So you may be confused of whether I should add 30 or minus 30, right? Let me try to explain the derivation of the new supply curve using economic perspective. So we have the original quantity supplied in utopia to be the expression 10p plus 50. And now with the import, the quantity supplied is increased by 30 units at any level of price. So this one would be the quantity of import. Apparently, we are adding 30 because we have the quantity supply from importing live chickens. So this is why the new supply curve will be given by Q equals to 10p plus 80. To find out the new equilibrium point, nothing special. We just type the original given demand and the new supply curve that I have just derived here, highlighted in yellow as well. We can find out the intersection point of the demand and supply to solve the new equilibrium price, $8.5, and new equilibrium quantity, 165. This is the comparative statistics due to change in supply. So let's move on to the next problem. Here, we are given the original revenue maximizing price and quantity to be this pair here. But to discourage smoking, the government has just set a per pack tax of $2 to buyers. So what would be the reduction in revenue maximizing quantity? So recall your knowledge in elasticity. So if we have the revenue maximizing point, it will simply be the midpoint of the demand curve. So the idea of solving this problem is as follows. If we can derive the original demand curve, we can then obtain the new demand curve after taxation. Finally, to find the midpoint of the new demand curve, and then we are able to find out the revenue maximizing quantity after the taxation. So let me show you what I exactly mean about the approach. Okay. Because the original revenue maximizing point is 40.22, this is the midpoint of the original demand curve. So with this, we are able to calculate the x-intercept and the y-intercept of the original demand. For the x-intercept, it will be 40 multiplied by 2, whereas the y-intercept will be 22 multiplied by 2. So with the x and y-intercepts of the demand curve, we have 2 points here, and we are able to derive the original demand curve. So let me shift my screen to GeoGebra and to solve this with you together. So let me type the points on GeoGebra first. We have the x-intercept 80 and the y-intercept 44. I can use the functionality in GeoGebra called line function, which is here. What you need to do is to collect the 2 points, and then GeoGebra will help you derive the original demand curve, which pass through the points here. Now we can take into account the per unit tax of $2, which will shift the original demand downwards by 2 units. Because we have the original demand function to be y equals to negative 0.55x plus 44. If we like to shift the demand curve vertically downwards by 2 units, then we will have the new demand function y equals to negative 0.55x plus 42. The green curve will be the new demand curve in this question. All right. Finally, we are going to find the midpoint of this new demand function. How can you do that? We can find out the x and y intercept of the new demand function first, and just focus on the x coordinate of point D, because we are trying to figure out something about the quantity side. The new quantity would simply be 76.36 divided by 2. Okay, the midpoint between DE. This means that the new revenue maximizing quantity is 38.18. Now we are ready to calculate the reduction in revenue maximizing quantity. Originally, the revenue maximizing quantity is 40. With the per unit tax of $2, the new revenue maximizing quantity becomes 38.18. So this is why we can calculate the reduction in quantity, 1.82. All right, so hope you understand the technique and the demonstration in GeoGebra. And we'll move on to the last problem in part A of this topic. We are given the demand function in log form. we are going to find the price elasticity of demand for a good X and also the income elasticity of demand for a good X. So let's start with the first part, the price elasticity of demand for a good X. Apparently, both the dependent variable and the independent variable in consideration, Px, are in log form. So this is why, as I've explained in the review part, the coefficient in front of log Px is automatically the price elasticity of demand because it has a constant elasticity at any level of price. So this is the first part, price elasticity of demand for a good X is negative 2.4. How about for the income elasticity of demand for a good X? Actually, something similar, because income, the independent variable in consideration, and Qx, the dependent variable, are both in their log form. So this is why the coefficient in front of log income is already the income elasticity of demand for a good X, negative 1.2. We have a constant income elasticity at any level of price. As you can see, it appears quite simple for this part if you understand the mathematical meaning of these coefficients. That's about the discussion for part A, and the remaining time of this video will be devoted to part B, in which I will discuss two problems. One about the perfectly competitive constant cost industry, and the other about the long-run quality adjustment due to an effective price ceiling. So the first question in part B is this one. We are considering a perfectly competitive market in a constant cost industry. We are given the demand and supply functions here. The question says that suppose there's an increase in demand such that each consumer's willingness to pay is increased by $10. Given that the initial long-run equilibrium price is $60, what will be the quantity traded in the market at the new long-run equilibrium? So how can you deal with this problem? So first of all, we need to derive the demand curve. How can you do that? We should expect demand curve shift upward by $10 to incorporate the increase in willingness to pay. I call the new demand as D1. Okay. So how can you obtain the new demand curve? Let me take this opportunity to go to GeoGebra together with you and to demonstrate a little bit on the graph. All right, so we have the original demand function as this thing here. And now we want to have the new demand function, an upward shift in demand. Because the willingness to pay is about price. So this is why we would like to incorporate this $10 next to Y, okay, next to the price. We expect the new demand function should be something like this. We just don't know whether this is a plus sign or minus sign, the direction of shift, okay? Actually, because the question gives you Q as a subject, the variable on the horizontal axis as a subject. However, you need to change something about the variable on the vertical axis, the Y, right? So this is why we need to perform the strange thing. If you like to have an upward translation, you should put a minus sign instead. All right. If you do not understand too much of this approach, or you find this a little bit counterintuitive, you may actually check in GeoGebra. Suppose you happen to put Y plus 10 as a bracket here. You will obtain a downward shift in demand, which is not what you expect, right? So this is why we should put Y minus 10 instead to obtain an upward shift in demand for the increase in demand. So we're going to find the market quantity traded in the new long run, right? Be aware, we are considering a constant cost industry. So what is so special about a constant cost industry? We know that in a constant cost industry, even when there's a change in demand or a change in the number of firms in the market, the marginal cost and average cost of production will still remain unchanged. What's the implication? The long equilibrium condition or the minimum point of the average cost curve would just stay the same. And this explains why the lower equilibrium price would remain at the same level, $60, as well as the long-run quantity produced by individual firm will also remain at the same level. So to find out the new long-run market equilibrium quantity, we just need to plug in the price of 60 back into the new demand curve to find out the answer. The corresponding quantity as suggested by this point would be the answer to this part. So let's do that in GeoGebra to draw a horizontal line y equals to 60 and to find the intersection point with the new demand function. As you can see, the new market equilibrium quantity in the long run is 2,150. So this solved the problem here. And yeah, I'll move back to the slide and we'll discuss the last question in this topic, which is about a long-run quality adjustment of price ceiling. So we are given the demand and supply functions here, and we have a price ceiling of $100 per bottle of vodka. So this is actually an effective price ceiling. You do need to check the effectiveness of the price ceiling, but suppose I let you know that this is effective. So what happens in the market? Let me draw a demand supply diagram here for you to briefly understand what is happening in the market. So we have the effective price ceiling below the equilibrium price. In response to the price ceiling, there will be quality adjustment in the longer run. So the suppliers are trying to reduce the product quality, and this would reduce the production cost of each bottle of vodka by X dollars, and at the same time, willingness to pay of the consumers is reduced by 2x per bottle. All right, so in the graph here, we'll have a downward shift in demand and also a downward shift in supply due to the quality adjustment. And in the longer run, the new demand and new supply would intersect each other at the original price ceiling, $100. So this question asks you, at the new equilibrium after the quality adjustment, what will be the market price and the market quantity? So to begin with, we need to derive the new demand and new supply curve after the quality adjustment, right? So how can you do that? Because seller's cost of production is reduced by X dollars per bottle of vodka, then we would like to shift the supply curve vertical downwards by X dollars. Because X is about prices, the cost of production is about prices, right? So this is why we would like to put the X next to the price. And be aware, this question gives you Q as a subject, the variable on the horizontal axis. However, you are going to change something about variable on the vertical axis and the price. So this is why we need to do the counterintuitive way. To put P plus X, we need to put a plus to obtain the downward shift. And similarly for the demand, because consumers' willingness to pay is reduced, then we'd like to shift the demand curve vertically downwards by 2x dollars. And we need to do the counterintuitive way, which is to put P plus 2x to incorporate a downward shift. If you find this hard to understand, you can do the alternative approach, which is to express the supply and demand function using P as a subject first, to take into account the reduction in production costs of the suppliers. Okay, we put the minus X here, and to incorporate the reduction in buyers' willingness to pay, we put the minus 2x here to derive the new demand and supply functions. Anyway, after deriving these new curves, we can move on to the next step. As I've just mentioned here, the new demand and new supply will intersect each other at the initial price ceiling, $100. So this is why we can plug in the price of $100 back into this demand and supply functions. And as you can see, we actually have a set of simultaneous equations in two unknown, Q and X. It's also put down here for your reference. So we can make use of the graphical method of solving simultaneous equations, which is to plot the two equations of straight line in GeoGebra and then find out the intersection points between the two straight lines. Here, I'm not trying to plot a demand-supply diagram in GeoGebra. I'm just using GeoGebra as a tool to help us solve a set of simultaneous equations. So X and Y in GeoGebra does not represent Q and P in the demand-supply diagram here. Okay. So for X, I will use the horizontal variable X in the coordinate plane to replace that, nothing special. While for Q, I will use the variable on the vertical axis, Y, to replace it. So this is why I put Y equals to the thing here and Y equals to the thing here in GeoGebra to find out the equation of straight line. The intersection point between these two straight lines will give us the solution. We have X equals to 21 and Q equals to 50. And we can now conclude the problem here. The market equilibrium price in the long run is $100, the initial price ceiling, and the market equilibrium quantity is 50 that we have just solved in the simultaneous equations. So that's all for the coverage of this topic, function transformations. Thank you.